The surface of modern Mars is a frozen, desiccated wasteland, with an atmospheric pressure hovering around 6 to 7 millibars, less than 1% of Earth's. Any pure liquid water exposed to this environment would instantly boil or freeze solid. Yet the physical geography tells a different story. Deep outflow channels and expansive valley networks carved into the bedrock prove this planet once hosted a massive, water-rich environment. The mechanism that drained this world lies in its planetary spin. Over millions of years, Mars has experienced extreme shifts in its obliquity, or the tilt of its rotational axis. This diagram outlines how that tilt drove planetary-scale climate shifts. When comparing the present-day obliquity to the 35-degree average tilt over the last 20 million years, a clear cycle emerges. During periods of high obliquity, increased solar heating forced the polar ice caps to rapidly sublime. This aggressive evaporation pushed massive volumes of water vapor into the upper atmosphere, where chemical processes split the molecules, allowing lightweight atomic hydrogen to permanently escape into space. Over deep geologic time, this tilt-driven atmospheric bleed stripped the planet of an estimated 80-meter-deep global equivalent layer of water. The surface dried out entirely, leaving a central question: where did the surviving water go? The search begins in Utopia Planitia. From the surface, this vast northern plain appears perfectly flat, rocky, and utterly devoid of moisture. But the Shallow Radar Instrument, or SHARAD, aboard the Mars Reconnaissance Orbiter, is designed to see past this dusty exterior by measuring electromagnetic echoes from deep underground. By mapping subsurface structures, SHARAD revealed a massive, continuous layer of sediment hiding just beneath the regolith, a formation scientists call the latitude-dependent mantle. This cross-section shows what the radar actually found. Beneath a thin veneer of dust, this mantle is composed of between 55 to 85% concentrated water ice. Mars never lost its oceans completely. The catastrophic thinning of its atmosphere simply forced the remaining water underground, locking it into a massive, planet-wide subterranean vault. Even with massive kilometer-thick glaciers buried underground, the sheer cold of the Martian crust means that pure liquid water still cannot exist at the microscopic level among the sand grains. The catalyst that changes this is a class of highly toxic salts called perchlorates, which are distributed universally throughout the Martian soil. When calcium perchlorate dissolves, the freezing point of the mixture drops aggressively, plummeting to -75 degrees Celsius. Due to this extreme tolerance, perchlorate crystals perform deliquescence. They pull water vapor directly from the atmosphere until the crystal destabilizes, melting into a liquid droplet. These highly concentrated liquid brines remain stable for hours at a time, forming and flowing through the shallow subsurface, despite the freezing temperatures around them. The toxic regolith and extreme cold do not entirely prohibit fluid water on Mars. Instead, the specific chemistry of these salts creates the exact thermodynamic loophole necessary to keep liquid water moving through the dirt today. The presence of subsurface ice and transient liquid brines directly controls where astrobiologists look for signs of ancient life. To test these environments, the Curiosity rover was sent to Gale Crater, navigating directly over clay-rich rocks that formed during deep periods of water-rock interaction. By heating and chemically breaking down samples of this clay, Curiosity's onboard instruments detected a surprising variety of complex organic molecules preserved within the rock matrix. Among the dozens of chemicals identified was a specific nitrogen-containing molecule whose structural framework resembles the core building blocks of DNA. Further analysis confirmed that these sedimentary rocks act as a dense physical shield against cosmic radiation. Complex biological information, including fragments of DNA, can be preserved intact as biomarkers for over 100 million years inside this material. The extreme atmospheric loss that transformed Mars into a freezing desert simultaneously turned it into an optimal deep freeze preservation vault. The organic record is locked in place, undisturbed by tectonic recycling or active surface weathering. The organic molecules Curiosity found on the surface have been slowly degrading over millions of years of trace cosmic radiation. To find truly pristine, complex biological structures, the search has to move deeper underground, directly into the ice and brine layers. The European Space Agency's ExoMars-Rosalind Franklin mission is designed to reach this untouched zone, targeting the ancient hydrothermal deposits of Oxyoplanum. The rover is equipped with a 2-meter deep drill, built to bypass the radiation-bombarded surface zone entirely, cutting into the protected crust. At this depth, ancient organic material is shielded from cosmic rays, stabilized by the surrounding ice, and potentially mobilized by microscopic brines. Mars is a dormant, frozen archive, holding an intact biological record, waiting for us to dig deep enough to read it.